Hello, our team today would like to present you our project called Sign Language Recognition. Today we're gonna talk about the aim of the project, algorithms and used LA methods, implemented solution and data used for that, results, comparison with existing benchmarks. So, aim of the project. The primary goal of this project is to develop a real-time system capable of recognizing and translating sign language gestures into text using a webcam. The system aims to accurately detect hand movements and classify them into predefined sign language symbols.
The algorithms and used LA methods. So first we capture the video and we do the landmark extraction. Video from camera is captured using OpenCV library, and landmarks are extracted in real time using MediaPipe hands library and represented as a 3D vector where XY are like basic coordinates and Z is the depth. We extract 21 points using MediaPipe. After that, we do the translation magnitude calculation. To achieve the translation invariance, we shift all the landmarks so that the wrist becomes the origin. So the wrist becomes the 0, 0, 0 coordinate. And by using this formula, we shift all the other points. After that, for each point, we calculate the distance from the wrist to it using the Euclidean norm. After that, to achieve scale invariance, we normalize each translated vector by dividing the maximum Euclidean norm across all landmarks. Here's the formula. And then the normalized vector is given by this formula. These steps ensure that the landmarks are invariant to the hand's position and scale. Next, we do the feature vector extraction, which we will further use in order to understand the gesture. So first, we do the angle computation. Given a wrist point and a fingertip, we calculate the distance. And after that, we calculate the angle between the y-axis and between this vector using this formula. After that, between each 5 fingertips, we calculate the distance. It will be our next 5 elements in the feature vector. We calculate them by using the Euclidean distance. And so as a result of this step, we get a feature vector with 5 angles for each finger with the y-axis and with 5 distances among 5 fingers.
So now I would like to explain you the PCA method. This algorithm implements the PCA method for dimensionality reduction, and the goal of PCA is to project high-dimensional data into a lower dimensional space while preserving as much variance as possible. We implemented such functions as transpose, covariance matrix, power iteration, PCA feed, and PCA transform. So now I would like to explain it mathematically. Principal component analysis uses mean centering, matrix multiplication, eigenvalues, eigenvectors, and projections. First of all, we use data centering. Each column is centered by subtracting its mean. Given a data set, X, where n is the number of samples and m is the number of features, and the center matrix is defined by the formulas that you can see on the screen. And then we use covariance matrix. The covariance matrix, sigma, describes the variance between all pairs of features. Each element represents the covariance between feature I and j. Then we use eigenvectors and power iteration. To find the principal components, we compute the eigenvalues of sigma corresponding to the top k largest eigenvalues. The eigenvectors v satisfies this formula, and the power iteration method is used to approximate the dominant eigenvector by repeated multiplication and normalization, and it is defined by this formula. Then, once the principal components are computed, the original data is projected onto them to reduce dimensionality. Given center data point and eigenvector, the projection set is defined by this formula, and this projection represents the coordinates of the data point in the new lower dimensional space. And the final reduced data matrix X is defined by this formula, where Vk contains the top k eigenvalues as columns. This transformation retains the direction of greatest variance in the data.
And now we move to the most interesting part of our implementation. It is the gesture prediction using Canon classifier. What it generally does, the function calculates the Euclidean distance between 2 points. It measures how far apart 2 points are in the feature space using this formula. But what are these vectors? So we have the data set, and for each letter to recognize, we have another set of images. And for each of these images, we run our feature vector extraction function in order to get the feature vector of each hand for the given letter in this data set. So each feature vector we extracted, we put into a JSON file, and later we use them for prediction. And now how the algorithm actually works for the hand when we show it. It computes the distance between the test vector, the feature vector we calculate while the hand is shown, and they're prepared vectors, and we calculate them by the Euclidean formula. After that, for each of the vector pairs, we store distances along with their corresponding labels. After that, we sort them by distance from the smallest to the biggest. After that, we select the labels of the car nearest neighbors, and after we selected them using Kynan classifier, we choose the most common label among the all labels we got, and use them as prediction.
Okay, now for the implemented solution and data used. The first methods are translation, magnitude calculation, and normalization. Each of these algorithms implemented by writing method subtraction for the translation, vector magnitude for the Euclidean norm, and scalar division for the scaling. And applying every method of above, we are getting a normalization. Here is the code, so it's pretty simple, so let's go to the next. The next is feature of vector extraction. So in order to implement this algorithm, we firstly implement functions to find distance between vectors and finding the angles. Then we plan them to find distances between fingers and angles between them. Next is PCA. In order to implement it, we first need to implement some more functions to fully write it, and those are transposing metrics, finding covariance metrics, and power iteration. Transposing metrics using zip function in Python, we can easily transpose it as done below. The next is finding covariance metrics. Here we implement it using just 3 loops, so it's pretty simple. The next is the power iteration. Here we used a threshold method, so that the distance between previous and current eigenvector will be small enough. In our implementation, we used e to the power -6. The next, we need to initialize a PCA object with the number of components, mean, and list of components. Then, to feed our data, we first need to find the mean vector function to find the mean of every column. Then before predicting gesture, we feed it for our training data. Now I will explain it in more details. So we compute and store data mean, center the data, build the covariance matrix, reset our component list. For each principal axis, we extract the dominant eigenvector using power method. Also approximated the eigenvector of C with a large eigenvalue. Then we store it, estimate the eigenvalue. Then we deflate the covariance matrix. This subtracts out the variance captured by our eigenvector. So the next iteration finds the next largest eigenvector. Now, thirdly, we're using PCA on a given gesture, so we just find the projection of it. Then for k nearest neighbors, first we need to initialize it and fit our Knan object with the number of neighbors, trained vectors, and corresponding gestures. Finally, we predict given gesture depending on training data. So we sort our distances between our feature vector and the training data, and define the k nearest, k smallest. Then the major labels of our gestures is a given gesture. So here are some results. As you can see, we recognizing an alphabet. So here is the D letter, and here we delete the letter from the keyboard.
So our dataset is the ISL alphabet dataset from Kaggle. It looks like this. So for each letter, we have a lot of pictures in order to extract the feature vectors and then compare them to the data we read from the video. They look like this from different positions to understand the gesture, even if it is shown like very, very far. Now the comparison with the existing benchmarks. Here on the screen, you can see the video from the GitHub repository we're comparing our approach to. Our approaches are basically the same. They have the same goal. They use the same implementations. But the main difference is that our approach uses manual feature extraction from hand landmarks, making it simpler and faster for the real-time applications, but sometimes with a bit lower accuracy, especially for complex gestures. In contrast, the GitHub approach relies on deep learning with CNNs, which automatically learns features from raw image data, offering high accuracy, particularly with intricate gestures. However, the GitHub approach is more complex, requiring large data sets and computational resources, and maybe not that fast for the real-time use. And so our team, it is Pavlosiuk, Hrynda, Denysova, and our mentor, Artur Pelcharsky. Thanks for your attention.